Dave, what's it like getting a phone call at the crack of dawn with this prize attached to it?
It's a wake-up call, and it's kind of surprising, and I couldn't understand the person talking to me because of the accent and because I was half dead, having just been asleep for a few hours. So.
And how long did it take to work out, to realize what was actually happening?
I think about half an hour, and then I went back to sleep again. And then I woke up and, oh, okay, that was real.
Okay, so the three of you have received the Kavli Prize in recognition for your work exploring the far reaches of the solar system, and specifically the Kuiper Belt. Jane, perhaps you could give us an idea of what is out there and the distance that we're talking about.
The Kuiper Belt is a population of icy bodies extending from, say, about the orbit of Neptune outward to we don't know where the outer edge is. We know it goes out to at least about 1,000 astronomical units. That means 1,000 times further away from the Sun than the Earth. These things should be, they're basically the remnant of the planet formation epoch. They just failed to make big bodies. So they just got the leftover material from the solar formation era.
And what made you look in this zone? We knew about the 8 or 9 planets, but you guys have been looking in this space beyond the 8th planet.
We were just puzzled by the apparent emptiness of the outer solar system. As you said, up until recently, we thought the Neptune or Pluto was the edge of everything that we knew about. And beyond that, there was supposed to be empty space until the Oort cloud. And we just were puzzled by that. Was it really empty, or maybe there were things, but nobody looked hard enough.
Why should it be not empty? What was the motivation for actually looking in a space?
We believe everything in the solar system came from the solar nebula, which is a disk of gas and dust, and these things collide and make the bodies, the planets that you see now. And it is unlikely that this solar nebula, this disk, had a sharp edge at about Neptune or Pluto. That's very unlikely. So, you know, it might taper off. It should extend further out. But why didn't we see things? So we were just puzzled, and so we decided to take a look.
And why was this a field that took so long to get started? Why is it very difficult to see things?
Things in the solar system get fainter very quickly as you go further out. Up until CCDs came along, photographic plates really didn't have the sensitivity. And when we started looking, that was still in the early stage of CCDs. So, you know, they just came on the scene, gosh, maybe 10 years ago. And so it was the right technology came along for the right question. So,
Dave, many of your colleagues must have thought this was kind of a bit nuts, that you're spending all this time in observatories looking into what looked to be empty space. How was your work sort of perceived by the community?
Yeah, I mean, basically, we wrote proposals to get, you have to write a proposal to get telescope time. So we write proposals to get time, and in a way we just say, well, we want to stare off and see what's there. And the basic reason was there's nothing there. And it wasn't the orbit of Neptune that we were concerned about, it was the orbit of Saturn, because beyond Saturn, at that time, I think we knew of just Uranus, Neptune, and Pluto. And the surprise was that that outer part of the solar system would be so incredibly empty compared to the inner part of the solar system. That was the basic issue, at least in my mind. Why is it so empty out there? And that was the question. But that doesn't have any great, you know, theoretical background to it, and so it's hard to motivate people. And then the other thing is that classical astronomers actually are not very interested in the solar system. So there's kind of there's a social class system based on redshift. The more distant the thing is, the higher the prestige associated with it. So snob value, basically. It's completely stupid, but that's the way astronomy is. And that means astronomers don't want to think about the solar system. And then planetary scientists have the opposite problem. They care about the solar system, but they really care strongly about nearby things to which you can send a spacecraft. And, you know, Saturn at that time was not one of those things. So the outer parts of the solar system fell in this gap between classical astronomy and regular planetary science, and nobody was working there. Nobody thought about it.
And was it the fact that no one was looking there, was that what attracted, well, I guess all of you to this space?
What attracted me was just this basic kind of dumb question, why is there nothing there? And the two possibilities being, there really is nothing there because there's some kind of dynamical instability. Those big planets maybe kicked everything out, and there was no research at that time to say that that was possible or not possible. Or just that it's an observational thing and nobody had looked hard enough to see these bodies. So it's just a really, really simple motivation. There's nothing grand, nothing overly theoretical about it. It's just the dumbest possible question. Why is there nothing there?
And it turns out that there isn't nothing there. There is something there.
Too many negatives for me to it turned out we got the good answer, which is there is something there.
Right. So how long did it take to staring at this seemingly empty space before you spotted that there was something there?
Well, I think from when we started, which was 86.
The observation started in 87.
86. Oh, really?
You started thinking about it in 86, but the first
okay,
observation
so anyway,
was 87.
something like that. To success in 90. The first one was detected in 92. So you can do the subtraction.
So 5 or 6 years before you spotted anything. That's quite persistent, really. That you spent quite a long time looking.
Yeah, and the reason was that the technology was developing as we were looking. So we do a survey with one detector on one telescope. And then, you know, a year later, 2 years later, there's a better detector, and it's twice as good or 4 times as good as the one we just used. So we would say, well, you know, we can just quit. This is a waste of time. Or we can take this more powerful detector and do it all again in a fraction of the time and then do more than we did before. And so we did that several times. So I think we just kept doing it until the technology caught up with us and basically allowed us to detect the objects. And after we got the first one, finding the next was easy. I mean, it's trivial. Then it's just a flood.
Did it feel like a bit of a gamble going down this route where you were looking for things which are incredibly hard to find and a long way away and quite dim?
But once you found them, we knew how to find them, so that was no longer a gamble. Before that, yes, that was a big gamble. But before, when we did not know if there really was anything, that was a gamble. But once you found the first one, then we know we can find more.
But it wasn't the only thing that we did. So we did more ordinary research as well. So this was an additional program. It's like a cool thing that we would do a little bit in secret. So sometimes we would steal time from other projects, steal money from other projects, things like that, to get the data. But we would have the other projects going as well, because in science you have to have this kind of continuous record of productivity just to stay in the business. And so you need to do more straightforward projects that will have a result, even if that's kind of boring by comparison with the discovery of the Kuiper Belt. So we did that. But this survey was going on in parallel, kind of in the background for many years.
Mike, perhaps you could tell us some of the things about what were found in the Kuiper Belt and the earliest large bodies in there. What types of things emerged?
At first, there were no large bodies, and that was one of the frustrating things about the Kuiper Belt. There were these, all these discoveries that Dave and Jane were finding were basically little point sources in the sky about which you could know almost nothing other than where they were and what their orbit was, which was a lot of information to learn.
What sort of size are we talking about here?
These were a couple 100 kilometers across, the bigger ones. But for the first almost decade of the Kuiper Belt, those really were the typical size that were being discovered. And that was, again, it was a technological reason. That was the sort of thing that you could discover if you went to a sort of typical size telescope with your typical digital camera and you went and stared at a patch of the sky. It's easy to find the common smaller ones instead of the more rare big ones. And I began in the field wanting to study the objects themselves, the properties of the objects themselves, and it was very difficult. And I thought, you know, let's see if we can go find some bigger, brighter ones to go study. And so that ended up being, actually, it's a very parallel in many ways, a decade later set of surveys from what Dave was just describing. We first started out with photographic plates in 1997, looking at big areas of the sky for the rare, bright objects. Did that for 3 years, found nothing. Came back with new digital cameras that covered bigger areas of the sky more quickly, and then started finding these large objects. And finally, from these large bright objects, we could use the telescopes on the Earth to actually study them in detail and learn about their properties.
And when you say large, bright objects, what sort of size are we talking about?
So the largest ones, when I think of large ones, I think of sort of 1,000 kilometers and up. Pluto is about 2,300 kilometers. There are a half dozen of them that are sort of that scale of an object. One that's about the size of Pluto, maybe bigger, maybe smaller. But those are the objects. For a long time, if you wanted to study properties of objects in the outer solar system, you sort of had Pluto to look at. That was the only thing that was big enough that you could see it in detail and study its surface and its atmosphere and its density and its moons. And now we had all these new objects that we'd found where we could actually start to understand the properties of all these objects put together. And just like Pluto had this wonderful story that you could tell by looking at the object itself. It sort of contained a little bit of the history of the solar system all in one body. And these other objects were the same way. They were a different little history. And by putting together all these objects, we've learned a tremendous amount about how the outer solar system acts and put itself together.
So one of the bigger objects comparable in size to Pluto was Sedna, which seems to have an extremely unusual existence. Can you just tell us a little bit about Sedna?
Yeah, Sedna is actually, I think, the most interesting thing we found out there. It's not the largest one. It's actually, in some ways, it's sort of like when I was describing all these other Kuiper Belt objects as too small to really know very much about. This one is so far away that we can know very little about it other than its orbit. But its orbit is so odd that we have already starting to learn a lot from the orbit. The strange thing about its orbit, it's on a very eccentric orbit. It's incredibly elongated. It comes in about twice as far away as Neptune is from us right now. That's as close as it ever gets to the sun. But then it goes out about 100 times further away. And it goes in a orbit that takes about 12,000 years to go around the sun. It's a very strange orbit. There's nothing else like it at all in the Kuiper Belt. In fact, we don't even think of it as part of the Kuiper Belt. It's part of whatever is beyond the Kuiper Belt. It's not attached to the Kuiper Belt.
So when you start seeing patterns and orbits that are like that, or in Sedna's case, it's unique. But how do you then begin to figure out how that happened? Because that is a very unusual orbit.
It's one of the most fun things about doing this sort of research is that you get to do it yourself. You found this object, you found the orbit, and now you have to come up with the explanation. You can't pick up your book and read what happened. And so you look at this sort of orbit and you go through everything you can think of. An orbit like this has to be, the only way to get an orbit like that is for Sedna have been perturbed by some large object in the solar system. But the problem is there are no large objects in the solar system that could have perturbed Sedna to where it is. So it means something else was around at some point.
When you say perturbed, you mean hit. So it was going around.
It doesn't have to get hit. It just has to get close and then get flung out on an orbit like that. Normally, you would get close to Neptune, and when you get close to Neptune, you get flung out on an orbit, but you come back to Neptune. You always come back to whoever flung you out. But Sedna never comes close to Neptune. It never comes close to anything. And so the question is, what used to be out there that's not there anymore? Or what's out there that we don't see now that we're still yet to discover?
And what's the answer?
Well, so just like I think with the earliest discoveries of the Kuiper Belt, when you find one object, it's easy to come up with explanations because you only have one object and you can make things up. And we have spent a lot of the last 6 or 7 years looking for more objects, distant objects like Sedna, and haven't found any. There will be more out there. They're just faint. They're even further away than the Kuiper Belt. They require even bigger telescopes. My favorite explanation for Sedna, which seems right to me, is that it formed in the earliest history of the solar system. It formed like a regular object that got scattered by Neptune, came back to Neptune, back to Neptune, back to Neptune. But sometime when it was out here, it got close not to another planet or something. It got close to stars that were in the vicinity of the sun. If the sun formed in a cluster of stars that were all very close together, those stars would have perturbed Sedna all the way out here and made it so it never comes back to Neptune again. And then it's just stuck. It's frozen in this orbit now that's never comes close to anything. The stars eventually all drift away and the sun is left alone, and Sedna is this fossil record of what happened in the past.
So you talk about fossil records, you talk about the history of the solar system. Jane, what does all of this research tell us about how our solar system formed?
It hasn't, well, changed a little bit. We used to think that, as I said, everything in the solar system came from the solar nebula, and that just things, lots of smaller bodies moving around, sticking together and growing bigger and bigger and bigger. And so that was a general idea, and it's still the basic paradigm now. It's just that finding these objects tells us that the past history perhaps were maybe more violent. There were more strong gravitational events that gave rise to these strange orbits. So we never suspected these things. We thought, okay, things collided and stuck and grew bigger and bigger and bigger, and we have the planets and we have the comets and so on. But then finding the Kuiper Belt and the different types of orbits inside it, and there's so many different types of orbits, and they all gave clues to different processes in the past. So now we went from a fairly well understood solar system to a badly understood solar system. So is that progress? I think so.
It's kind of like the Donald Rumsfeld. It's you go from known unknowns to unknown unknowns.
Exactly. That's just anyway. So what we found that it's a much more complex past than we suspected. And do we understand it? Not really. We see clues, and we're trying to decipher the clues.
Let me just say, the one thing that I think I was really impressed that you guys found back before I was really starting this is that you talked about the orbits of some of the objects. This big chunk of objects with orbits just like Pluto suddenly irrefutably told us that the giant planets have moved around since they formed. And as Jane said, we used to think, they all just form and that's just the way they are, nothing much happened. And the giant planets moved around. They didn't just form right there. They have been in very different places. Now we think about it and it just seems, yeah, of course they did. That's trivial. But I remember the first time that
planetary migration.
That sort of blew my mind.
Mm. I think that's the most important result from the Kuiper Belt, actually, is the identification of planetary migration in the solar system. Because what it means is the old models where people assumed the planets just keep going in circles and it's the same clockwork solar system, those models just don't apply. And as Jane said, there's a lot more uncertainty now because since the planets are moving, we don't actually know quite where they were in the past. And so within the uncertainties, there are quite a range of possible configurations for the solar system.
Do you mean in relative space to the sun, in their relationship to the sun?
The sizes of their orbits, the diameters of their orbits are now basically not completely free parameters, but they're changeable things. And that opens up the possibility that, planets could drift into orbits where they have very strong gravitational interactions with each other. And so, for example, a model that's been talked about a great deal in the last 5 or 6 years involves Jupiter and Saturn getting into a special configuration where they essentially shake the solar system almost to bits, almost 1 billion years after it formed. Now, we don't know if that happened. We don't have the evidence that it did. But the point is it might have. And so we're forced to consider kind of crazy models like that as being plausible now, whereas before we had Kuiper Belt objects, and we knew of these heavy so-called resonant populations, we didn't have to think about models like that. So that's been a game changer, I think, in the solar system.
Now, imagine a fantasy world in which grant applications don't need to be done and resources are unlimited. I'm going to ask each one of you this question in turn. What do you do next in that scenario?
For me, it's to build the survey telescope that we all would like to see built now. It might be like one that's already planned called the Large Synoptic Survey Telescope, but that thing is not yet funded. So basically what you want is, what I want is a telescope that surveys the whole sky quickly so it can identify moving objects, and it goes really, really faint so you can see small things far away. And it just keeps doing that for some long period of time, like a decade or something like that. And so with a telescope of that sort, we would increase the number of known Kuiper Belt objects from the present 1,500 to maybe, many tens of thousands, up to 100,000 objects, plausibly we could get. And we would get good orbits for all of them. And so we would be able to map out the dynamical structure of the Kuiper Belt extremely well. So right now we have spotty measurements, we look in this direction, we look in that direction, and we sort of guess what's in between. If we can do the whole sky in a systematic way, we'll get the first clear picture of the outer solar system. And the mystery to me is that nobody wants to pay for that, because that is fundamental. Understanding what's in the solar system seems to me the first thing you would want to do to understand the solar system. I mean, how can you understand it if you don't know what's in it? And so we basically just discovered most of the solar system in terms of volume occupied by bodies. And we need to explore that fully. So we need this survey telescope.
Jane, same question, and then Mike.
I agree with what Dave said. I think that would be the ideal thing to build. In addition, but there are things further out that conventional telescopes won't be able to see. I'm talking about things that thousands, tens of thousands AU, like the Oort cloud even, and we see things at the Oort cloud. That these are the comets in the Oort cloud are the most distant things that we know of in the solar system. We can't see them in the Oort cloud. We only see them when they come in to the planetary region. So we look at the enormous orbit and we say, the Oort cloud must exist. They come from the Oort cloud. But you can't see things in the Oort cloud, and we don't know the inner edge. We don't know the outer edge. So I would like to think of some technology that would be able to probe that kind of distance, and it won't be with conventional telescopes. And what is that technology? I don't know yet, but that's I'm thinking about it. I'm trying to figure out a way to probe that kind of distance.
Mike, unlimited resources, unlimited time.
I'm going to say yes to both of those first, because I totally agree. And I'm actually very excited about the LSST that Dave talked about. But that's maybe a decade away, and I'm not a very patient person. So if I had the unlimited resources and telescope time right now, the thing that I'm still most excited about is finding more of these very distant objects in this region beyond the Kuiper Belt where Sedna is. The large survey telescopes, even though they're going to be quite big, are not going to find many of those objects. They'll do very well in the Kuiper Belt, but not on that next region out there. So for there, you want large telescopes, the sort of 10-meter telescopes we have lying around, and big digital cameras on them, and a lot of time on the telescope just to do what we have all done, stare at blank patches of the sky and look for things moving very slowly across there. If you can find more of these objects where Sedna is, you're going to find more of these little fossils and eventually be able to put together the whole history of the birth of the sun.
Okay, I want to ask you about inspiration to round off. Both Mike and Dave, you mentioned the Apollo missions to the moon as part of the inspiration for you getting into science in the first place. What do you see, Mike, perhaps you could start, as being the inspiration for the next generation of scientists, planetary scientists and astronomers?
I have, sitting in Pasadena, California for the last month, watched just everybody's face light up as the Mars lander touched down on Mars. I think a lot of people were pretty dubious that any of this would work, and kids stayed up late watching it happen. They have Lego rovers. They go to the internet, look at it, every picture that comes down with their 3D glasses. I think that's going to be something that people in 20 years will look back and say, this is the moment when I thought, yes, I really want to go into science and study space and other planets.
Dave, what about Curiosity's up on Mars, but that's unmanned. Do you think there's a future for manned space exploration?
Well, it provides a lot of the excitement. So, it would be too crude to say that people want to see other people put their lives in danger. But that, in part, was really why Apollo was so exciting. So the idea, I barely remember, I was 10 when, or 11 when that happened. People went to the moon and landed. The idea that people were there was the key thing, right? They're actually very brave people doing an extraordinary thing. So that is hard to justify economically. It was done for completely political reasons. It was massively effective. It was the best thing that NASA ever did. It really fulfilled its true objective almost immediately, and NASA has been trying to recover ever since. I actually don't know what would be a comparable event. I don't know if there is a comparable event to sending people to another celestial body for the first time. So frankly, I seem a little underwhelmed by the idea of sending people to Mars. To me, it's kind of a rehash of the original mission to the moon. Much more difficult, I agree with that, but it somehow doesn't have the same edge to it, to me. So I don't really know what would be a comparably exciting event.
Jane, what do you see as the big inspiration for the next generation of planetary scientists?
I grew up in Vietnam. I had no idea when Apollo landed on the moon. We didn't have a TV. I didn't know.
Now, right?
Now I know. Yeah. Now I know, yes, that was a big deal. I kind of agree with Dave in the sense that I don't, in terms of science, sending humans to Mars is not going to achieve that much, because the challenge there would be sending people to Mars, make sure they're safe, bringing them home. That's the biggest challenge. So as in part of science, spacecraft, robot do so much better, and they don't worry about the heat, the cold, they don't worry about anything. I think in terms of inspiration for the next generation, I think the idea that the solar system, which we thought was our own little backyard where we knew everything, is not at all well understood. And it's our own backyard, and we still know, we understand, we found out now that it's very complex. All kind of funky configurations might have existed in the past that we didn't suspect. There's a lot of things to discover. And you know, and when we started out, we were just two astronomers. We didn't have the biggest telescope. We didn't have the best instruments. We didn't have funding. We just decided to look. And I think I'm not saying that we were the models that they should copy. We just said the idea that you can pose some questions that everybody will think very radical, stupid even, but you pose a question, and even if everybody laughs at you, and if you think that it's a good question, you can go after it, and you don't, you know, just two random astronomers with just modest resources could do it. You know, almost anybody can.
But the key is curiosity.
And perseverance. It might take a while.
All right. Well, Mike Brown, Jane Liu, and Dave Jewett, thank you very much.